Now, this is a chemistry show, and whether you like chemistry or whether you like science in general, it's very important that you be observant. So we're going to start with a test. I want to know, put your hand up if, when you came into the lecture theatre, you noticed the two television cameras. Okay. Right, well, all of you who put your hands up, you're all wrong because there was one television camera, so you need to check on your observation skills. Why is there a television camera here? Well, there's a camera here because Oxford University is going to make you all internet stars. This show is being filmed for iTunes, so in due course you'll be able to see yourselves all on iTunes. And I thought it would be a good idea, since we're a nice friendly bunch, if we started off by, I will count to 3, and then you're all going to have to turn around and wave at the camera and shout, "Hello from Oxford." Okay, can you remember that? "Hello from Oxford." Right? Do you think they can remember that?
We'll see.
Right. Okay, wait. Shh, 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 shh. Quiet. Quiet, please. So, it's going to be 1, 2, 3, and then you turn around and shout, "Hello from Oxford," and wave your hands, okay? 1, 2, 3. Hello from Oxford. Well, you haven't got the idea at all. People are meant to be hearing you in New York and Buenos Aires and Sydney and Toronto. And if you can't be more enthusiastic about this, you might just as well get up and leave. So I want a bit of oomph this time, a bit of noise. Can you manage that? Okay, so 1, 2, 3. Hello from Oxford. Better, better. So, this show is not going to be a magic show. In other words, Malcolm and I are not going to do something and say, "Oh, that was a bit of a surprise, I bet you didn't know what was happening there," and then move on to something else. There are going to be no tricks. And indeed, we're going to tell you what the science is behind most of the demonstrations. So when you leave today, you should know more than when you came in. You'll be a better scientist. But there is a saying in science, don't try this at home. Lots of these demonstrations you won't have seen in your chemistry classes at school, and there's a good reason for that. It could be that the chemicals are too expensive, it could be that you need specialized equipment, but it could be, and for some of the demonstrations it is, that they are dangerous. So please don't be tempted to rush home and try these in your bedroom or your kitchen or at the bottom of the garden. You can ask your chemistry teacher about them instead. And this is a nice peaceful demonstration. I've got a colorless liquid here and a blue liquid here, and all I'm going to do is to mix them. And, well, it's produced a sort of nice green color, but that's not terribly exciting. You've seen green colors before. You've seen color changes before as well, I'm sure. So what we'll do is just put this on one side, and we may come back to this demonstration a little bit later.
Right, I need 3 volunteers, please. Can you all make sure that you're allowed to be filmed? So, right, come on then. Stick over there. Come on. Yeah. Right, so as Hugh said, these are all experiments. So I need you to wear safety glasses, yep. There you go. And then the other thing is, because they're all experiments, there is a potential that it won't work, okay? So that's why I've got these 3 volunteers to do this first experiment, because it is known to be a little bit tricky. So what I'm going to do is, in the front here we've got a hot plate stirrer, yeah? We're going to stir it, and what I want you 3 of you to do is each one of you take one of these bottles here, all right? So you can have C, you can have A, and you can have B. And then what I want you to do is, so that the camera can see it, so you're going to have to kind of come round at the front here. I want the 3 of you to pour it in at the same time. Yeah? So come on then. Be brave. Right, sort of round here, so There you go. Like, make sure everybody can see you. Right, so at the same time, I'll pour. Come on, pour it in. Yeah, all at once. Right, so it's not very exciting, is it? Oh, wait a minute. So it's got... So what colour is it? So it's blue, it's sort of bluey purple, yeah? Does anyone know what that is? A bluey purple, yeah. Like, what colour is it now? What colour is it now? Right, so what's going on here is what we call a clock reaction. So it's a bit chaotic, so we don't know exactly when it's going to change colour. But what's happening is that we've got the purple stuff. There's two things in there that are reacting together to make C and D. And then what compound C is actually causing the reaction to go faster. So it's a catalyst. But then as the reactions keep going, because there's like 13 reactions going on at once, it then regenerates compound A and B, which is why you've got the colour change. So thank you very much, volunteers. Can I have my glasses back?
Okay, now, if I tell you that this next demonstration, one or two of you, just one or two of you, might not be able to see this demonstration, can you see what it might depend upon? Any ideas? No? Good idea, but no. Okay, I've got a special chemical here, and this is, as you can see, a very dark chemical. So in order that you can see it properly, I've got a white light, and I'll just shine this white light through it. Okay, so what colour is it? Yeah, it's clearly red. It's obviously red. But it's actually also green. If you look in the neck, you can see, and if you look at where the bubbles are, you can see that this is green, but it's also red. Now, this chemical, this is not a trick. We don't do any tricks. This chemical is actually really green and red at the same time. Okay? Now, this raises two questions. One, of course, is, well, usually red plus green makes brown, so why isn't this stuff brown? But the second and more interesting question is, how can it possibly be red and green at the same time? So it's not magic, no. So has anybody got any explanation for this? How can it be red and green at the same time? Yeah? Yes? No, it's only a single chemical here. There's not two chemicals. There isn't a red one and a green one. Well, the explanation is really quite interesting. To what colour are our eyes most sensitive? Green. At last somebody said green. Our eyes are most sensitive to green, and if you believe that we evolved by growing up many, many hundreds of millions of years or hundreds of thousands of years ago in an area which was forested, it would be very important that our eyes could see green because the trees and the grass around us would be green. So our eyes have probably evolved to see green very well. This solution here absorbs light, and it absorbs blue light really, really strongly, and it absorbs green light a little bit. So if I shine light through this, if I shine white light through this, and white light, of course, contains all the colours that our eyes can detect, if I shine white light through this, the blue light is absorbed very, very quickly. So I shine some white light through here, the blue light is absorbed almost immediately, and what gets through the solution is then red plus green. And because our eyes are very sensitive to green, we see the green. But if the light has to pass through a very large amount of solution, so it has to go from one end of the solution to the other, more and more and more of the green light is absorbed, and eventually no green light is left, and so what we see is red light. So this solution is genuinely both red and green at the same time. There's only one chemical that is red and green, and it's called dichromic, literally two-color. It's not very many chemicals that we know that are like that, but this is one of the nicer ones. Okay, let's come back to the solution that I started with. You'll recall that this solution there was originally a colourless solution and a blue one, and I mixed them together and they went green, and now this has gone red. This is quite a clever solution because this can do arithmetic. This can divide by 2. Let me show you. So here is the old beaker, and let's just divide this in two, and they're different colours. Okay, now there's no trick. There isn't anything sort of stuck on the bottom of this that's reacting with this. It's only one solution, and yet it makes two different colours. So you might think about that, because we'll come back to this in a moment, but it's Malcolm to...
Yep. So can I have 3 more volunteers, please? Come on, man. One more, yeah, come on. Right, so same again, safety glasses, just in case. Right, it's a pair for you. Where's that? Oh, there you go, number 3. Right, so what I've got in front of you, each one of you's got one of these. That's yours, that's yours, okay, and that's yours. Right, and what I want you to do is you're going to take the lid off this, try and make sure it's as soft as possible. Right, so you're going to take the lid off these and you're going to add these chemicals, but I want you to all do it at the same time. Right, and as you add the chemicals, put the lids back on and then shake it and hold the lid in place, because I don't want you to get anything on your skin, okay? So maybe it'll be there. Like, let's see, if you all put yours down, there's yours, there's yours, there's yours. All right, so I want you to all do it at the same time and hold it up so everybody can see. All right, 3, 2, 1, go. All of it, chuck it all in. And then put the lid on and shake it. Oh, you missed that. Right, so can everybody see what's happening? Yeah, so what we've generated here is an example of what's called cold light. Okay? It's coming. So what we've got here is an example of what's called cold light, or chemiluminescence. So as the name suggests, it's chemistry to make light. And as you can see, they're all different colours. The reason it's called cold light is if these 3 touch it, it's cold, yeah? There's no heat coming off it. So normally if you had a light bulb, it would also generate heat at the same time. So that's why it's called cold light. Now, can anyone think of an example where you would use this in real life? Glow sticks, which we just happen to have here. All right, so these are the same thing. So what you've got is a little vial inside that you snap, and the 2 chemicals mix, and then you shake it, and you get light. So you ready to catch? There you go. You can all have one each. Right, do you want to put them down? Right, we've not got any big ones left, but we've got some little ones. So you ready to catch some?
Maybe at the end.
Yeah, I'll just give them a couple. Right, so I'll just throw these ones out now. Right, if you come and see me at the end, yes, because we've got to get on. If you come and see me at the end, we've got some more, and you can get one then, okay? Right, so just going to move on to the next thing. Right.
Quiet, please.
So,
Quieten down.
when you think of school teachers, like, keep it clean, because remember we're being filmed. When you think of school teachers, what's the word that comes to mind? Horrible. Boring? Can you think of some nicer things, maybe? All right, so when I think of school teachers, I think of one word, and that's rich. Yeah? You know, they get all these school holidays, they're always on a break, and they get paid loads of money to look after you lot. Yeah? So, with bearing that in mind, is there any school teacher in here that'd like to give me a loan of £20? Oh, we've got a volunteer. Oh, that'll have to do. Thank you very much. Hugh.
Okay. You got the tongs? No. And I'm going to got an ordinary J-cloth here, and I'm going to soak this in the magic liquid. And then we're going to see if we can set light to the J-cloth.
There we go.
And we can. And it actually burns really quite well. But in the end, you can see it's not actually burnt, and yet J-cloths are made out of flammable material. And that's really quite curious, because you can feel, what does it feel like? It feels cold. Okay, well, that was sort of a bit of a failure in a sense, wasn't it? Because it's more fun when things go wrong. So let's try again. We'll put it back in the same liquid. And we'll use another match.
There we go.
And those of you near the front will actually be able to feel the heat. So that it's possible to make cold flames, but this is not a cold flame, this is a hot flame. This would burn me if I got too close to it, or if I put it...
Oops.
And so you can see it is sufficiently hot that it does actually eventually burn the J-cloth. There's a little burn there. Now, burning a J-cloth isn't much fun, but haven't we got something else we can burn? Oh, we've got a £10 note. So, well, that's disappointing. Let's give it another chance. It's not my money after all. So why is it then that the pound, this £10 note, doesn't actually catch light? What is it that's kept it? Yeah? Well, the reason this doesn't burn and the reason that the J-cloth doesn't burn is that the liquid that we've got here is a mixture of water and something that does burn, something that's flammable. So when we put that mixture onto the J-cloth, or when we put that mixture onto the £10 note, the water which doesn't burn keeps the £10 note cool, where the flammable material, the burnable material, evaporates off and burns around the £10 note. Now, of course, if we keep on burning more and more of this liquid, the £10 note will get hotter and hotter, and eventually it will catch fire. And a couple of years ago, I managed to almost destroy £20 of a primary school's teacher, 20 pounds that belonged to a primary school teacher, but fortunately the number on the note was left. And if you've got the number on the note, you can take the remains of the note back to the bank and they will give you a new one for it. So, it's yours, is it?
Right, so now I'm going to do an experiment using hydrogen peroxide. So, hydrogen peroxide is essentially, it's water with extra oxygen in it. So it's very, very oxygenated, and sometimes it can be found in the body, so the body has to deal with it. So, what we do is we have an enzyme called catalase, and if we mix these two together, what you can see is all that extra oxygen goes somewhere and it makes a big froth. Now, it didn't mix very well, which is why there's a bit of a mess in my beaker, but you can get the point. Like, it's actually just foamed up, and all these bubbles coming off are actually oxygen. Right, so we've looked at hot stuff. So now
before
we're
we
going to
get
look
to the cold stuff,
Sorry, I missed that.
Before we get to the cold stuff, we've got to go back to this solution. Remember, this was the divide by 2 solution, and it's still able to divide by 2. 2 different colours. So what's going on? There's nothing stuck on the bottom of the beaker here. There's no trickery involved, but this solution knows whether it's been divided in half or not. 2 different colours. Yeah. What? No? Any more suggestions? Yeah? What am I doing here? I'm mixing it with what? With air, yeah. The coloured chemical here is something called an indicator. Now, you've met indicators at school, perhaps, if you had acids and bases in your laboratory lessons. But this indicator tells us how much oxygen there is in the solution. And as I add air to the solution, what happens is it changes colour. And you can see when I've got a lot of air in the solution, it's a green colour. If I now put this solution on one side, there is a reaction that goes on in the solution, and that reaction uses up the oxygen. It's a reaction between glucose, sugar basically, and sodium hydroxide. And that uses up the oxygen in the solution. As the amount of oxygen in the solution diminishes, the indicator changes colour. And so eventually we go from green to red to a sort of browny colour to eventually gold. And we can make this cycle of colour changes work again and again just by mixing in some more oxygen.
Right, cold stuff now. So, who knows what air is made up of? Like, what's the air?
Nitrogen, oxygen, and carbon dioxide.
Okay, so what we're going to do is we're going to cool the air down, and we get this stuff. Like, I don't know if you can all see that, probably not, but yeah, it's dry ice. So what is dry ice? What's it actually made of? Right, so what I'm going to do, it's not water. No, look, it's actually carbon dioxide. So what I'm going to do is, hopefully this is not going to fuzz up too much, but I'll put it on here. Let's put this in here. Right, it's going to fizz, yeah. Right, so does anyone know what that smoke is, apart from this stuff that's coming up from before? Yeah, do you know what that smoke is? It's what? Coldness. Yeah, but what actually is it? What do you think it's made of? It's actually, what's happened is because the carbon dioxide is so cold that as it's going straight from a solid to a gas, and as it's doing that, it's giving out its energy. And what it's doing is it's actually so much energy that it's freezing the ice, the water in the air. It's actually, and this is an ice fog. So carbon dioxide is quite bad for us because of the greenhouse effect and stuff. So we won't dwell on this too much. So what we will do is move to liquid nitrogen. So dry ice is about minus 78. This is about minus 160, 150. Right, so let's start with this rubber tubing. So people at the front, feel that. Does it feel like normal rubber tubing, yeah? Happy with it?
Yeah.
No tricks?
No.
So I'm just going to stick this in here. We've got some liquid nitrogen. So what do you think is going on here? Right, so what's happened is because the tube was hot, as it's hit the liquid nitrogen, it's actually, the tube's frozen, it's given enough energy for the nitrogen to come off, we're getting water vapors again, and what's it done to this piece of rubber?
It's cold.
Well, apart from being cold,
It's frozen.
so it's frozen, yeah, so look. Yeah, it's actually sort of rock hard. Now, if we leave that to warm up, I'll get these guys in a couple of minutes to feel it again, and you'll see it's returned to normal. So, let's use this banana, right? So this is going to take a while to freeze, so I'm just going to put it in there for a while and leave it. I hope I can get it back out. So, something a little bit more dramatic. We'll take these flowers, So what do you think is going to happen to them? Right, we'll freeze them and see what happens. It's like being in Harry Potter. Right. Whoops. So, touch it. So, the difference between a living thing and like a bit of rubber is the fact that this is made up of cells, and inside the cells there's water, so as it freezes, the water forms ice, which punctures the cell walls, and that's why it goes all brittle. And like, there's nothing we can do about this now. It's gone. Yeah? So, moving on to a balloon. What do you think is going to happen to this balloon? It's going to pop. So what happens to the air when it freezes? Does it get bigger or smaller? Well, let me put it in and you can see. Cold. So what happened to it? It got smaller, didn't it? But look, as it's warming up, it's getting bigger again. So what's happened is the air's frozen and become a solid, which takes up less space than a gas. So why do you think it's a trick? Because what? So what happens to you when you get cold? You go blue? Nah, fair enough, you're too smart. The other one's in here. Yeah, but you can see that it has shrunk. It took a couple of minutes to get it to shrink. And as you can see, as I'm waving it around, my arm's blowing it up. Yeah, it's getting bigger. So we could do this like loads and loads of times. The only problem is, of course, is the fact that this is made of material, and as it gets stretched and relaxed and stuff, it can start to sort of get holes in it. So you couldn't do it forever, but you could do it at least 10, 20 times. Right, let's see where the banana is. Well, I'm just going to use these because I don't want to put my hand in here because it is quite cold, to say the least. So like, whoa. It's very cold. But as you can see, it's completely and utterly solid. So if you come up at the end, what you'll see is if we open it up, it's become more like a smoothie. Because like I said, the cell walls have all punctured and stuff. And finally, going back to our tubing, it's still cold, but so it's gone back to being bendy, hasn't it? See, look, you can't make it bang anymore. So that's why materials can get hot and cold, whereas we can't. Laser diode next.
Yeah. Do you want to do that subsequently, the block?
Oh, where's this? Do you want me to
Okay, scientists like to get rules. They like to categorize things. They like to observe experiments and then draw deductions from them. And I want to tell you now about a really remarkable thing that happened many, many years ago, long before any of us were born. There were some scientists looking at all of science knowledge, and you'll be aware from school lessons that there are some bits of science that are fun, and there are some bits of science that are a bit dull. There are some that are difficult, there are some that are easy, and so on. And these scientists looked at all of this huge array of scientific knowledge and noticed that there was a great big collection of science that was really, really dull. And so scientists wanting to categorize things said, we're going to have to give a name to this area, and so they called it physics. And so what I'm going to do is I'm going to teach you a very small amount of physics. There's a little laser here, and all I'm going to do with this laser is try to put the laser beam into this piece of plastic tubing. This is a hard piece of perspex, and you can see that it's hollow, but there's a little notch cut out of the top here. And I'm going to try to get the laser beam into the notch. And you can see that when I do that, the laser beam goes round in a sort of spiral. So what we're doing here is bending light. You might think the light goes round, only goes in straight lines, but in fact we can make light go round. So the light is trapped inside the plastic. It's not trapped inside the tube, it's trapped inside the wall there. Now, does anybody know how we use that piece of knowledge? Well, it's used in fiber optics. Fiber optics are the way that data from computers travels around the country, and fiber optics consist of very, very thin wires, very, very thin filaments of glass, and the data goes down the glass and is trapped in the glass in the same way that the laser beam is trapped in that. Now, if you think that piece of physics was dull, this is even worse. I should say, actually, physics is fun. Malcolm and I are sort of quite critical about physics, but there's an awful lot of nice science in physics. So I've got here a small light source, and what I'm going to do is just to swing this around. And when I swing this around, what do you notice? Yeah, the light's going on and off. Now, why is it doing that? Well, it's going on and off because this light is plugged directly into the mains, and you'll probably be aware that electricity in this country is called AC current. And AC current changes its phase many, many times. You probably don't know what a phase is, but it's a bit like the electricity sort of switching itself off and on many times a second. So if you were to get yourself a digital camera and you had your science teacher have one of these things, and they cost about 4p, and he or she was to swing it around like this at 1 revolution per second, and you got your camera and you exposed for 1 second, then you would see one complete circle of light, with lots of little dashes, and by counting up the little dashes you could work out what the frequency was of the mains light. So, as I say, physics actually does get more interesting than that, but we thought we ought to have some bit of physics in there.
Right, so all the experiments we've showed you so far are experiments that give out energy. So I'm going to show you one where it takes in energy. So what we've got is a metal, we've got a metal container on top of a block of wood, yeah? And what I'm going to do is add this chemical to it and give it a bit of a stir. Hopefully this is going to work. Probably not going to work.
You might need to have the more of it in there.
Yeah.
Okay, so while Malcolm is doing that, there is going to be one last demonstration for which I need a single volunteer. And it's you at the back there. Yep. You. Yes. Okay, I shouldn't have chosen somebody right in the middle of a row, should I? No, I've already got one.
What's that?
Hi, what's your name? Giselle.
Yeah,
Okay. Are you right-handed or left-handed?
right-handed.
Okay, this is Giselle. She's right-handed, and what she is going to do in a moment, once Malcolm has had a go with his demonstration there, is Giselle's going to play around with this. Now, this is our cattle prod, and what she's going to do is you'll find it very heavy, so you'll need to support it with your left hand like that. She is going to, if you press that black button there and hold it down, what she's going to do is to pass a substantial current through a little wire at the end here, and eventually that little wire is going to get red hot. So what shall we do with it? Okay, so what she's going to do, you can let go of that for a moment. What she's going to do is to do a test once Malcolm has finished with his stirring.
So, what it's done is it's frozen. There's a little bit of water underneath, as one of the people in the front said, and what it's done is it's actually frozen it to the brick, so you can't lift it. So look, I mean, it can't come off, that's why I can lift it like that. And you can actually do this in such a way that you could get it so it's strong enough to actually, if Hugh was feeling strong, he could lift me on that block of wood because I would be stuck to it.
No,
That's how-
no chance, Mark.
Anyway,
Okay, so this is the final demonstration, and Giselle is going to see if she can determine what's in these balloons. Okay? So somebody said air. Any other ideas? Well, there are various possibilities. Those of you who suggested air have been watching too many cartoons where a cartoon character blows up a balloon and he gets bigger and bigger and then eventually it floats off. That's not going to happen with air because, of course, there's nothing to make the balloon rise. So this is probably helium, or it could be hydrogen. And the way that we're going to test that is Giselle's going to get that really nice and hot. And when it's really hot, what you need to do is to touch the end somewhere about there. So you press the button and keep it away from the balloon to begin with. And wait until it's really, really sort of glowing nice and red. And I'm out of the way.
right, go for it.
You got the scissors.
So what do you think it was then?
Okay, so that was a bang, but not really a very good bang. And the reason for that was because the gas
Let me get
was
past
helium.
that. I'll do the lights. Oops.
You're going to do fine. Right, okay. So Giselle's really getting into this now. So what we're going to do now is, the helium was a bit sort of disappointing, really. So instead of having another helium balloon, this one must be hydrogen, because we know that hydrogen is lighter than air. But the good thing about hydrogen is that it burns. So what we're going to see now is whether this burns, and Malcolm's just going to put the lights down a bit just in case we have difficulty in seeing what's happening. So that again needs to get really, really nice and hot, and when it's really hot, just touch it to the balloon.
Is it hot yet?
If you can put the lights down now because it takes a while.
You would too.
Now, you might have thought that that was a bang. You might have described that as an explosion, but in fact it wasn't. It was really just a very rapid burning reaction. And what happens is that the hot wire sort of makes a little hole in the balloon, and then the balloon kind of unwraps to leave a ball of hydrogen, and then the hydrogen burns. And so what you get is a flame. So it wasn't really an explosion, it was just a bit more interesting than the helium. So in case you were asleep with that one, Giselle's going to do another one. This is the same. And so what I want you to do is to look and see that it really is a flame as opposed to an explosion.
That's a bit more vigorous.
Yeah, you're going to get some earmuffs. But so you see that although there was a bit of noise there, it wasn't really a bang, it was just a kind of a whoomph, and there was a lot of flame. If we wanted to make a proper bang, then what we need to do is not to use the oxygen that's around the balloon, but to put some oxygen in the balloon. and just by chance we happen to have a balloon that's got some hydrogen and some oxygen in. Now, this ought to burn more rapidly, but it's quite difficult to get the mixture right, so this may be a complete flop. We've already seen one complete flop with the burner. Maybe this is going to be a complete flop as well. But just in case there is a bang, you've got to do two things. Okay, so be quiet so you can hear me. Just in case there's a bang, you've got to do two things. Okay? The first is you're going to have to put your hands over your ears. All right? But if you do it now, you won't hear the second thing, so wait. All right? So you're going to have to put your hands over your ears, and the other thing that you have to do is to open your mouth. The reason that you need to put your hands over your ears, of course, is obvious, because if there were a shock wave, then especially the people who are foolish enough to sit at the front would get their ears ringing. And you open your mouth because you may know that there's a connection between your ear and the back of your mouth. And so if there were a shock wave, then if you've got your mouth open, the shock wave will reach your ears both that way and through your mouth at the same time, and your ears won't ring. The other... Quiet, please. Come on, quieten down.
Come on, calm down.
Now, our fine volunteer here is going to have ear protectors on, and they're very good ear protectors, so she won't hear anything else. The rest of us have to do, as I say, hands over your ears and mouths open.
Good.
Having your mouths open is great because it makes you all look like fools, but only I can see it. The camera's not going to see it. And Malcolm's going to have the lights off. So, hands over your ears and mouth open. Okay, everybody, you included, hands over your ears, mouth open.
There's another one.
Okay. So we've got to get rid of these balloons. So here's another one. Same thing. Hands over your ears, mouths open.
That was loud.
That's it.
Thank you.